All right, good morning everybody. I want to apologize for the technical difficulties. There was a pretty substantial mishap at the beginning of my lecture that runs into things immediately before this, and it kind of threw everything off. It included me launching the wrong lecture stream, so the link had to change. It was a nightmare. I am having a mild, panic attack right now, but it's all good. We'll get through it together, and this link will be circulated around. I apologize for the lack of communication in the last hour. I had set up a lecture announcement to auto-post, and I was not able to get to it to catch it before it auto-posted, so some of you were directed to the incorrect lecture. This has been a total mess, but we'll get through it together, and we'll wait a few minutes before everybody, as folks trickle in here to the new link. Issue was that I came downstairs to load up my load up my streaming machine down here, and it turns out that I had left a USB drive in, and it tricked my computer into thinking it didn't have an operating system. That took me right up until the very start of my first class to resolve, and then I have been scrambling ever since. Now, I also want to apologize and make a general announcement for the lack of communication in the hour immediately before this class. I teach immediately before this one. So I teach my Physics 204 class before this class starts. And so I will generally not be able to respond to emails and stuff like that. I will get back to my phone has been blowing up with, I think, 36 notifications for my email. That is delightfully terrifying. I will get back to everybody who sent me an email as soon as I can, which means shortly after this class. We are going to run over a little bit today. That is just going to probably be unavoidable because we're getting started 15 minutes late. Good morning, everybody. Thank you for your patience, and I promise you that this will not happen again. If it does, I will, beg for forgiveness. That seems like my best possible option at this point. All right, I am going to pull up the slides. The updated slides have been posted to the course Brightspace. If you are coming here from Dr. Tamaro's class and you do not have access to my course Brightspace, just shoot me an email. I will be happy to add you in as a as a read-only member, so you can get access to things like the lecture slides that I post, and as well as announcements regarding the YouTube streams and so on. There's a comment in the chat that is unrelated to this course, but it's actually a good reminder here. My previous lecture, 204, was just streaming, and so many of you stumbled into that stream and were like, "Oh, this is not the class I signed up for." You are correct; it was not. But the video has since disappeared off my YouTube channel. This is common. And it will happen to this lecture as well as soon as I am done. And I'd like to take just a moment while we wait for the last few folks to trickle in to explain why that is. I record these things live and stream to YouTube on the channel. You are only about 6 seconds behind where I am at right now here in my basement. But the problem is the live recording. Once I am finished, YouTube takes that live recording and subjects it to some processing. It does things like analyze it for adding closed captions and things like that. During the period where the video is being processed, it becomes unavailable on my channel. It will then get posted, usually within about a day, to the channel, and it will live there in perpetuity, so you can always go back and reference it. Now, it's important to note that this is precisely the reason why I provide you the direct links to the video. Because once I finish recording live, it is always accessible at that link. As soon as class is over, you can go back and rewatch it as long as you go to that link, even if it hasn't appeared on my channel yet. So like was just commented in the chat, the video disappearing is just a normal part of the YouTube process, so it can be compiled and made into a permanent video that will live on my channel for the future. All right. That said, let's check how we're doing. All right, we're up to about 70. I think we've caught most of the people. We'll probably see another 20 or 30 so trickle in, and that will be good. So let's go ahead and get started. I need to Did my camera work? There we go. We're back in Chapter 1. Now we are going to go ahead and pick up where we left off. I realized after Wednesday's lecture that I did things slightly out of order with the text, so I apologize for those of you who are coming here from Dr. Tamaro's class. The beginning of lecture today might be a little similar. I'm not sure how far you got, but I will be sure to cover anything else that remains at the end once we have had an opportunity to get through stuff. And it appears that my slides have not loaded. So today is just one technical bungle after another. Third time is the charm. Yeah, so there's another comment in the chat about the syllabus video not working. That is because I had to change the link, so I'll go in and update everything after the fact once I have finished this lecture and have time to get back to my computer. Okay. Oh, thank goodness. I have my slides again. So today we are talking about starting off with significant figures in scientific notation. And don't worry, I hate Sig Figs just as much as you do. But they are, in fact, quite a useful way for tracking uncertainties in numerical values. You know, we in physics do a lot of experiments, and we don't always know our results to the exact precision that we would like. Sometimes, in fact, we have to quantify how much unknown there is to the values that we cite, and Sig Figs are a way to do that. Now, some central comments about this is we're going to be talking about two things in the first half of this lecture. The first are significant figures. Anytime you have a physical quantity, a number, something you have measured, there is a value to that number, and that value is represented by some certain number of digits. So, for example, you know, we will often see in this class that G is equal to 9.81. And that is a special number that we'll get into starting next week, and that is measured in meters per second squared. Now, that value, 9.81, has 3 digits in it, 9, 8, and 1. Each one of those numbers is a digit. Some of those digits are significant, meaning they make a quantitative statement about the precision with which we know that number. Other figures, so for example, if I talk about a number like 0.03890, note that this has 1, 2, 3, 4, 5, 6, 7 digits, but not all of those digits carry meaningful information. And so that's really the difference between significant figures and just other digits, is that the significant figures tell us something about the precision of the number we're working at. Now, closely associated with this is the concept of scientific notation, which is a way of mathematically representing numbers that makes Sig Figs easier to work with and makes representing very large or very small numbers easier. Of course, I use easier with gigantic air quotes because if you're not used to working with scientific notation, it can actually be a little bit challenging at the start. Now, numerical values that are obtained by measurement, like if I actually take a ruler and I hold it up to something and I make a measurement, that measuring device specifies the precision with which I can make the measurement. And so the tools that we use to make measurements are going to have an impact on significant figures. Now, like we said on that last slide, the significant figures characterize the precision of a measurement or the uncertainty of a numerical value. And there are some rules that quantify whether or not a figure is significant or not. These are the sort of bullet points. Anytime you have a non-zero digit, like 1, 2, 3, 4, 5, 6, 7, 8, or 9, that digit is significant. So anytime you have zeros that are between non-zero numbers, 2001, 2001, those zeros are in between significant digits. Then those zeros are themselves significant as well. And I think maybe what I'll do here is I'll come down and I'll point the line that I'm talking to. Leading zeros are not significant. So if I have 0.00009, none of those zeros carry any meaningful information. In a number containing a decimal point, trailing zeros are important. If I have the number 1000, 1000, those zeros might not be significant. But if I have 1.000, those are. In a number with no decimal point, trailing zeros are ambiguous. Hold on one second, folks. I have no way of... I'm getting an interruption. Just 1 second, folks. So I'm going to jump off this camera and just take a moment to write these down. And, write those down and internalize them. OK. Crisis averted. All right. Let's see some examples of how these things fit together so we can kind of see how this works out. Here are a bunch of numbers. Some of them have certain numbers of significant figures and others have different numbers. And we're going to go through these one at a time to count how many sig figs there are, and we are going to indicate why those digits are significant. Starting off at the top, that one's easy. 3 is a non-zero digit. All non-zero digits are significant. There is one digit there, so there is one significant figure. Similarly, 347 has 3 non-zero digits, so there are 3 significant digits here. Now this next one is a little bit tricky. We have a leading 0 and a trailing 0. And it turns out we have 3 significant figures here. The decimal with trailing 0, so that means to say this 0 is to the right of the decimal, so that's significant. But leading zeros, this black one over here, are not significant. So we only have 3. Similarly, there are 2 leading zeros in the next number, so only that 7 is significant. By contrast, we have a 0 in the middle of some other ones here, so those 703 gives us 3 significant digits. The leading zeros do not count. Now, this one down here is 250. This has a trailing 0. Is that significant or not? Actually, we don't really know. That's kind of the problem. When you are imprecise with how you write your digits, that may or may not be significant. We don't know. So what we suggest you usually do in that case is either write the number in scientific notation so there is absolutely no ambiguity, or just put a decimal point at the end of it. Putting that decimal point there really clarifies whether or not that 0 is meant to be significant or not. Now, once you have an idea for how significant digits are tallied, we want to also kind of get a feel for where they come from. And we mentioned that one of the places they come from are measurements. So let's measure something with an imprecise tool. In this case, a ruler with millimeters. We're going to measure the width of a coin with a ruler. Now, it's a little hard to make out, but if I zoom in here, we'll see if I just come on over and I kind of really just squint my eyes a little bit, it looks like that coin is maybe somewhere between 1 and 2 millimeters wide. Hard to say which one for sure, but just eyeballing it, it's a little closer to 2. Now, this ruler has an accuracy of millimeters. It doesn't make sense to measure something with a ruler with something more precise than millimeters. That wouldn't be a measurement, that would be an estimate. And we are interested in measuring this coin. So we have to round it to the nearest tick mark on the coin itself, 2 millimeters. Now, this has one significant figure, because we only know that it is approximately 2 millimeters wide, and 2 is a non-zero digit, that's one number. We can actually improve our precision by, instead of measuring 1 coin, measuring 17 coins. When we stack up 17 coins, we see that they end up being about 28 millimeters in total. Note that this carries 2 significant figures. If I then take those 28 millimeters and I divide by the number of coins, I get a fractional value that is a better estimate of the width of a single coin. But note, when I do that calculation with my calculator, I get a whole lot of digits here. How should I round this off? Do I know this to the precision of, let's see, that's millimeters and then micrometers, nanometers, picometers? No, my ruler is not that precise. So instead, I need to define some rules for how to do multiplication and division with significant figures. And the general rule for multiplication and division is this. When you multiply or divide numbers, the result should have the same amount of sig figs as whichever input number had the fewest number of sig figs. So if, for example, I were to multiply 2.2 times 3.98654, my result would be, I don't know why I picked such incredibly difficult numbers that I actually have to plug it into a calculator, but there you go. This gives us 8.770388. I round that off to the number of sig figs that each thing has, 3, 6. So since 2.2 has 2 sig figs and my other number has 6, I round my result off to whatever the smallest number there is, which means I would have to round this off to 8.8, and the rest of these are not useful information. So applying that to our coin example, the stack of coins has 2 sig figs. The number of coins, although you might be tempted to say that has 2 sig figs, that's actually a pure number. That is an exact number. It's precise. Exact numbers do not limit sig figs. So you can think about pure numbers as having an infinite amount of sig figs. Well, 2 is much less than infinity, so that means I have to round my result off to 2 sig figs, 1.6 millimeters. But sure enough, this number is a lot more precise. Instead of the 2 millimeters we were stuck with before, we used canny measurement to get a higher precision value for the width of our coin, 1.6. I could play this game more, measure a stack of 100 coins to get maybe 3 sig figs or something like that. And you'll play this game a bit in your homework, which, by the way, is posted on Sapling. And there is one question that's really weird. If you get caught off guard by it, don't worry about it too much. I need to talk to Dr. Tamaro about that. The very first one talks about like binding energy and the mass defect of something. I'm pretty sure that was mistakenly included. We'll see. I don't know. Maybe he mentioned something about that specifically in his class, but certainly I did not, so I need to check with him. But otherwise, you'll be doing lots of work with sig figs in there. OK. Now, the other rule that we have for sig figs is how to work with sig figs during addition or subtraction. And that's different. Addition and subtraction, the result should have the same number of digits to the right of the decimal point as the input number with the fewest digits to the right. So to put that simply, if I have a number, let's say 3.198, and I add 4.2 to it, I get 7.598. I find the number with the fewest digits to the right of the decimal point. That is definitely 4.2. I basically then just draw a line right down here, and I say, nope, I got to get rid of everything to the right of that. Now, that definitely means I should round this up in this case, but suffice to say, that's how you determine sig figs in addition and subtraction. Now, a good example of that would be whether or not, if I take my daily vitamin, or for me, it's actually my daily allergy pill, and that, say, allergy pill has a mass of 15 grams, and if my mass is 69 kilograms, does taking that pill change my weight in any meaningful fashion? And the answer can be answered with sig figs. Rather, the answer can be found with sig figs. Now, 69.0, note, has 1 digit to the right of the decimal, whereas 0.15 kilograms has 3 digits to the right of the decimal. I have to keep whichever one is smaller. 1 is smaller than 3, which means I have to round my answer off to the first digit to the right of the decimal, which in this case means my end weight is rounded to 69.0, which is the same as my initial weight, which just indicates that the weight of the mass of, my mass is the same as it started as, which just indicates that the pill that I took did not appreciably change my mass. It is too small to really count. And now the reason this is important is because when I get on the scale and it says 69.0 kilograms, what that's really saying is that your mass is somewhere between 68.5 and 69.4. I'm sorry, that's not quite right. What this is really saying is 69.04 and 68.95. What it's actually saying is your weight is somewhere between those two numbers, and so all of this extra information here in the 0.015, it's outside the precision that the scale is able to measure. Okay. Now I do want to take a moment here to remind you of that statement I made about pure numbers and talk about it in a little bit more detail. Some physical constants are known to a certain amount of experimental accuracy, and we can specify the number of significant figures. For example, this is off the top of my head, so I apologize if I get this wrong. Gravitational constant is like 6. I'm actually not going to write that down because I went out of my mind as soon as I started writing. But several constants are really only known to 2 or 3 or 4 decimal points, and so you can specify how many sig figs they have. Other constants are known or are defined either to extreme accuracies or are pure numbers. So two examples of that are pi, which is known to millions of digits, so it will never limit your number of sig figs. Or, for example, the speed of light, which is a definition and a real pure number. These things will not change your number of sig figs. We often round these numbers off, though. And how you round your pure numbers and your physical constants should be to round them as to not limit the number of sig figs in your result. So what I mean by that is, let's say you have these numbers as your input. You're doing something, maybe you're multiplying these two numbers, and this number has 3 sig figs, and this number has 4 sig figs. Let's say you need to multiply these by pi. Well, you should make sure that you're not limiting the number of sig figs in your result, which means you should have at least as many sig figs as your most precise number. So I should round pi off to something no less precise than this, because 4 is at least 4. Don't use fewer. If you rounded pi off to 3.1, well, now that would only have 2 sig figs and you would limit your result. We don't want to do that. Instead, to play it safe, you should preferably use a few more than you need. Round pi off to 5 or 6 sig figs, do your calculations, and then round at the very end. Note that some of your calculators will have very highly precise values built in, and you can use them, so you don't need to worry about this. So instead of doing 3.14159 in your calculator, you can just use your calculator's value for pi. Okay, let's see. How much time do we have left, and how many slides do I have left? Yeah, okay, we can do a quick example with this. So we have someone named Yana who has a mass of 53.5 kilograms, including her clothes, and we want to know what her mass is if she puts on a 114-gram hat. So we'll set up this problem by reminding ourselves what we're doing here, and we are finding a total mass. So that's going to be capital M, meaning our total mass, is going to be the mass of Yana, M sub y, plus the mass of the hat, M sub h. This is addition, so we know that when adding or subtracting numbers, the rightmost decimal place that is retained is the rightmost decimal place of the least precisely known quantity. So we know, in order to do that, we need to figure out which one of these is most precisely known. But the problem is, these two numbers are in different units. So we need to convert the mass of the hat to the same units as Jana. So we do that by taking 114 grams and we do a unit conversion like we talked about last class. We know that the conversion factor, we want to convert from grams, so grams need to be in the denominator, so they will cancel out, and we will end up with kilograms. Then we just go to one of our tables, we look it up. I happen to recall that 1 kilogram is 1,000 grams. I get that from scientific notation. A kilogram, kilo is the scientific notation for 1,000. So I have that conversion, which means that the hat is 114 grams. Sorry, kilograms. At this point now I can add these two numbers together. My total mass is 53.5 plus 0.114. Those are both in units of kilograms. And when I add those together, I get 53.614. But note that my least precisely known number has one digit to the right of the decimal, which means those extra things over there are not going to contribute. I need to round this off to that third decimal point, or that first decimal point, and so I get 53.6. So when we reflect here, we note that the hat does change Jana's mass. So this is different than the vitamin. But we know the increase in mass to the 1,000th of a kilogram, but we only know her mass to the 10th of the kilogram. So our result should be to a 1/10 of a kilogram. As a side note, when you're interpreting significant figures, there is one thing that you'll run into in this class occasionally, and that you'll sometimes get graphs like this one. We're not going to make a big deal out of it, but it turns out there is a sort of way to think about how to get significant figures from graphs. For the purposes of this class, if you're reading a value off of a graph, if it is precisely known, great. Like if you're given a function and you can plug in that function, you can get the exact result, good, use that. But if you are estimating a value, just try to estimate to 3 sig figs, just as a rule of thumb. Most of the things in this class that we do will have either 2, 3, or 4 sig figs. So reading your graphs to 3 sig figs is a good guess. Or rather, is a good sort of habit to get into. All right. One more thing I want to mention is scientific notation. We talked about it a little bit last class by talking about the scientific prefixes. I want to mention here today why it is that it's valuable. It is most useful for quantifying really big or really small numbers. And a good example of that is the radius of the Earth. There is a comment in the chat when writing a mass that isn't exact and using sig figs, once you round, would you use the approximate symbol instead of equals? So it kind of depends. The question is basically asking, if I come back to this thing, should I instead, would it be more correct to write it like this? And it's a little bit of dealer's choice here. I would say in practice, no, it's actually fine to leave the equal sign. The reason being is that unless the number is precise, then all numbers that we use are approximations. They're all either limited by measurement or limited by estimation, or they're just limited because we have a certain number of sig figs. And so since all of the numbers we're using end up being like this, an equal sign is fine. If you were really uncomfortable with it, you can indicate that this is an approximation because you rounded with this, but neither of these is more correct than the other. In fact, when we write scientific papers, we have a very specific way of specifying this. And what we would actually say is, is we would insert some, say, scientific uncertainty, maybe something like that, to indicate that this is unknown to a certain value. But this is beyond the scope of this class, so you don't have to worry about it. You can just keep using the equal sign. This is also, so there's a question in the chat, and this is a very good question, in fact. How do we know what units to use in this particular problem? I got sloppy and I neglected it. The answer is that at this step, you actually have a choice. You can do this problem in either grams or kilograms. You can do the unit conversion in either direction. Both of them are correct, as long as you label what your units are. I made the decision to convert it to kilograms, and so my answer is going to remain in kilograms the whole way down. So my final answer would be in kilograms here. Excellent question. Okay. Like I was saying, back to scientific notation. Radius of the Earth is a big number. It's a little less than 6,400 kilometers, or 6,370,000 meters. Now, this is, one, a difficult number to write. It's also a difficult number to track. It also has that problem of ambiguous zeros. Are these significant? Are they not? There's no decimal point here, but we don't know for sure. So instead, we express this in scientific notation. And we do this through multiplying by grouping. We take this and we recognize that the important information up front here is the 637. This can be rewritten by basically rewriting this number as 6.37 times a million. That will give us 6.37 million. Now it is this number here that we can come in and we can count how many zeros it has. 1, 2, 3, 4, 5, 6. And so we can rewrite that through the magic of standing in front of what I'm trying to talk about. We can rewrite this as 10 to the 6th. Because you can double check this on your calculator. Doing scientific notation, easiest way I found to do it is just literally count the number of zeros. And then that's your exponent. So that means that this number is equal to 6.37 times 10 to the 6 meters. Note that if I were to use a scientific prefix, this would be 6.37 megameters. But note, there is no ambiguity in the number of sig figs here. 10 to the 6th, that is exact. That's a pure number. It doesn't limit my results. 6.37 clearly has 3 sig figs. So my result here has 3 sig figs. So not only does scientific notation allow us to express very large or very small numbers concisely, it eliminates the ambiguity from trailing zeros and provides us a shorthand notation that is easier to read and sometimes easier to write. So there you go. At this point, we have a brief aside. Then actually we're more or less done for the day. That brief aside is, and then I'll go back and sort of fill in a comment about dimensional analysis. The comment is actually about your calculators. You have to be super duper careful when you're plugging scientific notation into your calculator. To illustrate that fact, let's try to evaluate this fraction. 5 divided by 2 times 10 to the minus 6. Now I'm going to show you 3 screenshots from a calculator. The first one is incorrect. I've just typed in 5 divided by 2 times 10 to the minus 6. I've just written this down exactly as it's written. 5 divided by 2 times 10 to the minus 6. Quick comment. There was a question in the chat. So only 3 sig figs in this one? Yes, absolutely. This only has 3 sig figs. OK. Here, I've just punched this in. 5 divided by 2 times 10 to the minus 6. And I get this number. But this is incorrect. Your calculator interprets this expression incorrectly. What your calculator is actually doing in this case is it's just reading it from left to right. It's saying, it reads, take 5 and divide by 2, then multiply by 10 to the minus 6. So this is actually giving you this number, which is different than what we're looking for. A correct way to plug this into your calculator would instead be to enclose the denominator in parentheses. This is telling your calculator, no, no, you got to do parentheses first. Do the 2 times 10 to the minus 6, and then divide 5 by that number. That should be a minus 6. I would like to call your attention to the fact that these are 2 very different numbers. This is 2.5 million. This is 2.5 millionths. Note the minus 6, whereas here it is positive 6. This can be a huge difference, and if you're not used to plugging scientific notation into your calculator, you may run into this yourself. It's worth noting, though, that many calculators have a built-in way of handling this that does it smartly. This last entry down here is also correct, but note that the way this is written, 2 times 10 to the minus 6, looks a little different than 2 times 10 to the minus 6 up here. That's because for this answer, I used this button on my calculator. This button down here does scientific notation in a way that respects the rules of order of operations. Now, I do want to mention that it is my personal preference to overcompensate. I include more parentheses than I think I need just to make sure I'm really doing it right. So just be careful and be aware of this. If you want to see an indication of just how messed up this can be, I refer you to a Twitter meme that broke the internet last year. In 2019, this viral math problem left the internet stumped. And I will encourage all of you to pause right now and figure out what that answer is. Just go ahead. Plug it into your calculator if you need to. In fact, I encourage you to plug it into your calculator. Do that now. Pause and go. Right. Thanks. Now that you've paused and done that, there are allegedly 2 answers here. One where we do the parentheses first, so that's 4. Then we do multiplication. That's 2 times 4 is 8. So then we get 8 divided by 8 equals 1. But there's another answer where you still do the parentheses first, so 2 plus 2 is still 4, but then you do division. 8 divided by 2 is 4 times 4 is 16. And in fact, depending on what calculator you plugged it into, you may get this result. There was a question in the chat, which calculator would you recommend for this course? One, I would say, is a calculator that gets this problem right, whatever that means. So I just prefer a regular scientific calculator. You could use like a fancy calculator like one of the TI-89 graphing calculators, but you won't ever use the graphing features, so like why spend $150 on something like this? Of course, this one is old. Like, look at this. This is from like the prehistoric Stone Age when I was in high school. You probably have fancier ones now. I actually use, in this class, this Calcio calculator right here. I quite like it. It's super cheap, and it does everything you need it to do. It has the ability to write out the stuff on the top and give you a number down there. So that's probably my preference if you're looking for cheapness. If you're really looking for rigor, you get this. Now, coming back to this viral meme, it ultimately boiled down to which type of order of operations thing that you learned and whether or not you stuck to it. PEMDAS is parentheses, exponents, multiplication, division, addition, subtraction, and that's what's commonly taught in United States schools, or at least it was up until Common Core rejiggered things around. And alternatively, there's BEDMAS, which is brackets, exponents, division, multiplication, addition, and subtraction. Note that the order of multiplication and division is what's swapped. This is taught in a lot of UK schools and a few schools in the United States. And interestingly, depending on how you type this into your calculator, if you just type it in blindly, like you just do 8 divided by 2, parentheses 2 plus 2, parentheses, different calculators will give you different responses. And that's weird. Math's not supposed to do that. But the reason it does that is because this is not a math equation. This is wrong. It's so wrong. The problem is that this is an ambiguous expression. They intentionally designed this so different calculators would give you different things. There is a freedom of choice. When you're doing multiplication and division, they have the same order of preference in order of operations, meaning you can do multiplication first or you can do division first. At their heart, it's the same process. So they have equal rank. And so if your math formula can be changed by changing the order of that, then you've written an ambiguous expression and you need to clarify what you meant. And if you want proof of the fact that ambiguous expressions are a known issue, here is a clip, an excerpt from Physical Review. It's the major scientific journal that is run by the American Physics Society. This is where I publish many of my papers in their various journals. And in their guide for authors, when they're talking about when you are writing out fractions, they explicitly say, they tell you to insert parentheses in ambiguous situations. For example, do not write a/b/c. Write this in an unambiguous form, such as parentheses a/b/c or a/b/c. Because it turns out these two have slightly different interpretations. This one gives you a over bc, whereas this one gives you ac over b. And you need to specify what that is. So, let's see, to Page AM doll, no, -10, see me after class. Bad math. Good math. Really, this is something that you should be aware of. So there is a point in the chat where that there was learn that if there's multiplication and division where all that's left, you just work the problem from left to right. Yes, that is the sort of rule of thumb. But importantly, that process where if you have an unambiguous, or rather you have an ambiguous situation, and then you just work from left to right, that is the customary way of doing it, and that's how most calculators are programmed. But, and this is important, that is a convention. And not everybody uses the same convention, which is why it is always best to leave absolutely no ambiguity as to what you mean when you are writing something down. Good. This was a fun little thing. Really perked my spirits up after an absolutely disaster-filled morning. Now, if you are here from my class, you are done for the day. You can take off. If you are coming in from Professor Tamaro's course, I recognize that the book actually has dimensional analysis after this discussion of Sig Figs, so that's probably what you came here for. So I'm going to take the next 5 or 10 minutes to go through the dimensional analysis section of these lecture notes again. If you were a little bit confused on Wednesday about dimensional analysis, and you have the time to stick around, I encourage you to do so. We're just going to go through those slides again so everybody's on the same page. The question in the chat is, what is the final answer here? Is it 16 or 1? And the answer is neither, both. It's an ambiguous expression, so it depends on your convention. The correct answer is to write it unambiguously. So there's a little bit of brain food for the day. OK, dimensional analysis. OK. So like I said, if you don't want to go through this again, you can take off, and I'll see you on Monday, where I promise like 90% fewer technical difficulties. I'll fix the bright space after class, and I'll see some of you for one-on-ones today. If you want to stick around and learn about dimensional analysis, so we're all caught up, I want to mention I'm going back to the idea of measuring things with quantities. And those quantities usually are measured in units. I measure the distance from here, my house, to URI in miles, for example. But importantly, quantities also have dimension. That represents the quantity's fundamental nature. For example, the height of a tree is a distance. You measure distances using things like meters or miles and so on. The duration of a movie is a time. Time is the dimension. The dimension of time is often measured in units of seconds. Similarly, the amount of matter in something, its dimension is a mass, which would be measured in the units of kilograms in this class. Like I said, each dimension can be expressed in various units. We'll use SI, but there is some notational stuff that I really want to emphasize here. Quantities, meaning like the variables that we use to describe quantities. Something's mass, something's speed, something's position. We represent those with italicized symbols. So you always see a slant when we're talking about a variable. By contrast, units are represented with non-italicized symbols. But this can lead to some confusion because we have lots of variables and lots of units, but not a lot of letters. So sometimes we reuse them. A good example of this is the letter T. T with an italic slant is representing a quantity, and that represents several different quantities in this course. We'll see it as temperature in chapter 14 and 15, a period of time like around chapter 8, or tension in a stretched rope around chapter, say, 6. Similarly, if you go on to Physics 112, you'll see T, note that it is not italicized, used as a unit for the magnetic field called a Tesla. So just here, the letter T can represent at least 4 different things, and if you go on past this course in physics, it can represent dozens more. So context is very important when you're trying to determine what a symbol means. Now, the dimensions that we talked about have 2 real applications in this course. Sometimes we refer to dimensions without referencing specific units. For example, we say distance divided by time instead of kilometers per hour. But also we use it to check that our equations are correct, because all equations must be dimensionally consistent. The dimensions on one side of an equation must be the same as the dimensions on the other. And the process of confirming whether or not an equation has dimensional consistency is called dimensional analysis. And that's the last topic for this section. To see it in action, what we want to do is we want to classify quantities by their dimension and then manipulate the equation to make sure that it makes sense. So instead of making sure this one makes sense, let's say I tell you that d is a distance and t is a time, but I don't know what a is. I can use this process of dimensional analysis to figure that out. I'm going to replace my variables with their dimension. D is a distance. That equals 1/2 times whatever the dimension of A is. We don't know, so I'm just writing that down as a placeholder. There's a comment in the chat about seeing capital T for temperature and lowercase t for time. That is true. Capital T is used for a period of time during oscillations, just to clarify that for the question in the chat. Now, we don't know what the dimension of A is. Oops, let's come back here. But we do know that T is time and that time is squared. Now, the first thing we're going to do is we're going to note one-half is a pure number. It has no units, so that it also has no dimension, so that's not going to contribute. And then we treat this like an algebraic expression. We divide both time sides by time squared. And what we are left with is that the dimension of A is a distance over time squared. If we were to replace those with units, distance might be measured in meters, time might be measured in seconds, but it's time squared. What we can do is we can go back to our table and say, look down here and say, oh, wait a minute. Oh, here's meters per second squared. That variable A must be some type of acceleration. And sure enough, in this formula here, A does represent the acceleration, and you don't need to know that yet. We're going to talk about that next week, but this is an example where dimensional analysis allows us to infer something about a variable. Other than that, that's basically all there is to dimensional analysis. Hopefully you did some unit conversions in Dr. Tamro's class. If not, feel free to pop into my Zoom office hours basically immediately after this class because we are more or less done. The book has a nice write-up of dimensional analysis. It also has an example that you can work through if you're confused. Otherwise, folks, we will call it here for the day. I have a bajillion and one emails that I have to go respond to and a meeting that I am now 1 minute late for. I will touch base with the folks of you who are in my class via Brightspace later this afternoon about the many things that are up in the air. If you do not currently have access to my course Brightspace and you would like to be added, just shoot me an email, robcoin@uri.edu, and I'll be happy to add you to my Brightspace so you can get my course announcements. Thank you very much for your patience today, folks, and I'm very sorry about the confusion. We will see you next week, bright-eyed and bushy-tailed on Monday morning with the correct lecture link and the correct lecture slides and the correct time, and all of this stuff will be resolved. Until then, I'll see some of you later this afternoon. Otherwise, enjoy your weekend. Bye-bye.